Hello, everyone. My name is Bro Chen. I'm a first-year PhD student at Emory University. I'm here to present our paper titled "An Infectious Disease Spread Simulation to Control Data Bias." The paper includes three other authors. One is my advisor, Andres, and Taylor and David. Our work includes two main parts. One is the infectious disease simulation, and another one is the bias data generation. I will first introduce the simulation and then we may go through the generated dataset. Here is our simulation. On the left of the screen, you can see a map, including buildings, roads, and dots representing the agents. This simulation is based on an existing partner of life simulation, in which agents go to work to make money, go to restaurant to eat, go home to sleep, and go to the recreation places to make friends. On top of that, we implemented an infectious disease model. We color-coded the agent by their infectious disease status. Currently, you can see most of them are still white, meaning they're still susceptible. Some of them are red, meaning the infectious, and the blue ones represents the exposed. On the left corner, you can see we're currently reaching day 2, and let us fast forward to some day later to see what happened. Now we're at day 24. Here is the epidemiological curve. You can see we've already passed the peak and most of agents now are recovered. There is this loss of infectious disease model. What makes our different is the bias data generation. In addition to use the OpenStreetMap to generate the roads, we also used census data to inform our agent generation step. For example, if a region has 30% of population with age over 50, then an agent from that region would have a 30% probability of being over 50 years old. With that information, we can tell an agent to report or not to report by the controller here. From this example, an agent with age 50 to 80 would have 80% chance to report, otherwise it will be 20% of chance. We also implemented another model considering all types of biases together. We implemented the model based on a logistic regression model, and the intercept and odds ratio can be controlled here. Now we can go to the data generated by the simulation. Here is our generated data. Let's take a look at the agent's attributes first. All the attributes are collected in this file, and including their gender and their race, and also include their reporting rate calculated from the logistic regression model. We need to highlight again that these attributes are not random chosen, but informed by the census data. Then this is how our bias disease data looks like. The first several lines represents the initial steps. In these lines, most of agents are still susceptible, and at some point later, at age 35, the first agent becomes exposed at the restaurant, and then also another agent exposed at work. The first agent becoming infectious is at day 2 at midnight. Based on this line, we can see the agent will report considering the logistic regression model, and he will also report based on the gender and income, but not report based on the age and race. Here's another example. This agent will also report in the logistic regression model, and he will report on age and gender, but not in income and race. Now we can analyze our dataset. This is the Jupyter notebook we use to plot our data. We use the same file to plot the graphs in our paper, and this file is also available on GitHub. Now let's take a look at our just generated data. We plotted the distribution of age over 50 as an example, and we also plotted the percentage of reporting cases considering the age bias. This is pretty much all of our presentation. We hope that researchers and health professionals may find these datasets useful to evaluate their infectious disease spread prediction models, to understand the robustness of their models to data bias. We also provide instructions to help users to simulate their own study regions. In this presentation, we used downtown Atlanta as the case study, and we'll also present San Francisco and Guangzhou Tianhe in the VODB.